Troy Veitenheimer from NTest.
Thank you, and again, thank you for everyone for coming. Again, the company that I represent is NTest, and my topic is remote fiber test systems and monitoring systems. Again, for people not familiar with remote fiber test systems, it's a server-based system in a NOC setting, and it continuously and automatically tests the physical fiber. So when we were talking about the breaks or the cuts or attenuation that may be introduced into a network, the system continuously monitors that by using an OTDR, which when the system is first installed or running properly, it sends a trace and it saves that trace. And then it continually, through the use of the OTDR, the software, and the switches in the system, it'll switch fiber to fiber to fiber, round robin. It'll take the physical characteristics of the latest trace and compares it to the reference trace. And if there's a deviation at that point, then there'll be an alarm at the NOC, and the alarm will be sent to all the appropriate people that are responsible for taking care of a problem like that. The alarm would indicate basically what the problem is. Is it a fiber break? Is it attenuation? Is it just slight degradation? It'll indicate the likely cause. So it could say a cut, or it could say human error, because based on the trace, if the break were to occur where a connector is in a central office, it will come up and say likely cause, human error. It's at this location in the central office, so you can go and fix that. And it'll also tell you like the time or the location on a map. It'll also show that as well, and I can show that. That's part of the presentation. And it'll say the severity, like a critical cut or a minor problem, increased attenuation, things like that. And this can all be controlled either in the NOC or from a remote location. That's the name, remote fiber test. Okay. Now, there's a lot of advantages of the current or of RFTS over the present mode of operation. And basically, the present mode of operation, when a service failure occurs, the technicians start to troubleshoot the cause and the fault by evaluating alarm data and trying to reestablish communication. So typically, you'll get an alarm in the system, and it'll AFCS. So basically, if there's an alarm, just to run through the present mode of operation, they'll first check to see is the transmitter transmitting properly. If that's yes, and if it's going to, let's say it's not a complete pawn all the way to the end, let's say there's a node further down the system and there's a receiver at that node, it'll then check, is that receiver working? And if the answer is yes, well, they'll try to reestablish communication again. If there's no communication, then they'll discover that this is a physical fiber failure. So at that point, the maintenance crew, they'll gather their test equipment and they'll get in their truck and they'll travel to the nearest point of presence where they can access that fiber and check it. When they get to that location, you got to find the proper port. Make sure you don't disconnect another fiber, possibly causing another outage, and then you do your OTDR test. The OTDR test, it provides an optical trace, which will indicate the distance from that point to where the problem is. And then that information is relayed to the NOC, and then they'll go through their documentation and compare that distance and get a physical distance, and then they'll tell the maintenance people it looks like it's on the corner of Broadway and 5th. And then they'll dispatch to that location and look around, and there'll be a backhoe or a tree falling over or something like that, and then they'll start their repair. So obviously the big situation there and part of the challenges and limitations to the present mode of operation is the extensive time and resources that are being used to determine, first of all, the actual cause of the problem. Is it equipment or is it the physical fiber? and then, where the maintenance personnel can access the problem or access to check the problem. Obviously, driving to the locations if you're in a metropolitan area and it's during rush hour or times like that. It takes a lot of time to get to that point. Then relaying that OTDR information back and forth between the central office and the maintenance people. And then again, driving to the actual location. Sometimes there's situations where they may be in the suburbs and they have to drive into the city to find the or to access the point, and then they have to drive back to where they were to actually fix the problem. And then, of course, like I said, there's added risks of removing the wrong fiber when you do the test, which could bring down another fiber. And how can AFCS help? When testing the network, when the break occurs, the OTDR takes the trace, and the alarm will show the physical location of where it's at. So here you got your equipment ports and then your outside plant, and you've got a 1x-N optical switch and the remote fiber test system here. And it's just continually testing these fibers. Through the use of WDMs, you can test your active fibers, or sometimes they also have just a dark fiber within a bundle that they'll continually monitor. And the theory there being, if something happens to one of the dark fibers, it's also happening to the other fibers. There's also, this is with a 1x-N switch then, where you have your remote fiber test system, testing fiber after fiber after fiber, just a round robin, 24/7, as I mentioned earlier. Or you can use a N/M switch, in which case, if there's a fiber break, you can reroute the active fibers to a redundant path and bypass the damaged fiber. And in that situation, the RFTS will then continue to test the other fibers, and it'll skip the fiber that's damaged or broken, so the maintenance people can repair that fiber without having a pulse of light going through the system. Here's how it shows on the map. So again, as I was saying, the test system, it's continually testing the system. When suddenly there's a break in the fiber, here's your, I'm just going to walk away, your reference trace here in black, and then it sends another trace, and there was a fiber cut in this location. So you have a deviation from the reference trace. It then sends the alarm to the appropriate people, and in the menu here, everything is green except for the fiber that's broken is now red. The effective fibers below are red as well, and the route shows up in red, and it shows the break on the map. You can zoom in, and you can see the exact location there on the street level. And this can also be downloaded or uploaded into Google Earth, so you can see the location, a satellite-type view. So the technical benefits, you have a non-intrusive 24/7 surveillance, automated alarms for immediate notification and identification of the faults and their locations. You can switch around the faulty fibers and the equipment ports. You can identify physical problems before they occur. The alarms based on attenuation level. I mentioned I was from Minnesota, and it's starting to get cold there. We had a carrier that had an inconsistent problem with certain fibers would all of a sudden, the customers would complain they're getting loss of signal, and they'd get alarms, and then the problem would go away. And they had a very difficult time finding that location, because by the time the test people were able to test that fiber, the problem had gone away. And it turned out what the problem was, it was a train trestle over a river, and there was a conduit with the fiber inside, and water would leak. The conduit had a crack in it, and the water would leak inside, and it would freeze at night. It would squeeze the fiber, cause the circuit to fail, and then in the morning, the sun, they'd get the alarms, they'd get the complaints, the sun would come up, and it would melt it, and the problem would go away. Then it would leak out, and it didn't happen like every year, but it happened just occasionally. And with RFTS, they realized it would alarm, it would save that trace, it would show it on the map. The next day or whenever they got there, they could come in, see immediately where the problem was, and they could drive there and fix the problem. There was another example, kind of a proactive example for a cable TV carrier. And what they had was they had also an inconsistent problem. Customers would complain, and they were trying to find the problem over and over and over again. And they installed RFTS, and what they were able to do, same kind of situation. They had these complaints. They looked at their records, and here they had an alarm at night. Everything was running fine, but it saves the alarms, said the location. They drove out to the location, and here there was a tree that was growing. It wasn't against the fiber at that point, but when the wind was blowing, it would blow against the cable, cause attenuation, and degrade the cable, or degrade the signal. So they were able to say, oh, there's the problem, and trim it. So before there was a complete failure. So a little bit more proactive there, where they get the alarms before there's a total failure. And then report generation. It's all automated, so you have the alarm history, you have specific alarms and events and system status. It helps in service level agreements and things like that to show your fiber has been, especially if you are selling or leasing dark fiber. You can continually monitor that, and you can show that the fiber has 0 failures or X amount of failures due to what reason, and so you have a very good record keeping that way. Saves operation costs and improves turn-up of new services. Dramatically reduces fiber downtime when there's a cut, and I've got overhead coming up on that. And also security. We have on a military customer that they use it, they have their reference traces, and they're more concerned about taps and intrusion into their network. So this would indicate if somebody tapped in, there's a new attenuation level in the fiber, they can go and investigate that sort of thing. The financial benefit, and to the bullet point in the last overhead, reduce network downtime. This is an example of a customer. They keep very close data on their network. They don't have RFTS on their entire network. They have a system where they determine the amount of data and the amount of information and revenue and various things that's going over a fiber, and they will add to RFTS. They will add RFTS to those fibers as their budget allows and as the amount of data and information over that fiber increases. But they keep very close track. So this overhead just shows their data of 27 cable breaks without RFTS on the right-hand side. The time to locate the break can take several hours. To dispatch the crew, it takes further delay. And their average outage, and that doesn't mean necessarily outage because it could be routed the other way, depending on the network and where the break is, as we were talking about earlier. But their average outage, or their average time that fiber is cut before it's completely repaired without RFTS is 9.7 hours. With the RFTS, the breaks are located in less than 6 minutes. They know exactly where the break is, and that's the big cost savings, obviously. Then the crew can dispatch directly to that location. They're on their way in less than 14 minutes. They monitor all of this. So their average outage is less than 3 hours with RFTS. It's just under. It's like 2.9 hours. But obviously a tremendous savings, and there's been a few situations now when we were talking about redundancy. We keep pretty close track of these, where there's been double cuts. There's been a cut on one side, and if you've got 9 or 10 hours to repair that, and then there's a cut on the other side within that time, and then you got customers that are totally out of service. So if you can shorten that repair time, it's very important. Benefits, quantitative and financial benefits. The return on investment, it's of course dependent on the data value of the damaged fiber, the maintenance and technician costs and things like that. We have different models or sheets that, or calculation spreadsheets that you can enter your information and see the cost savings there. But customers have documented 70% reduction in downtime, network downtime. As I was saying, proactive and preventive maintenance, eliminating the downtime, the tree blowing against there, freezing, thawing, those kind of things. 70% improvement in subcontractor repair costs, the people that have subcontractors do this kind of work. We've got a customer that has a lot of cable going under sea in the Caribbean, and they outsource all of that. And now they're able to say, just pinpoint exactly where the location is. Actually, it's a very interesting case study where they're able to, originally they had helicopters had to fly to like an oil rig well and send their OTDR trace to find, because the fiber would go up and around and through that as a point of presence. And now with RFTS, they know exactly where it is, and they can send the ship out to do the repair. So it's incredible savings. They said the first cut, the system paid for itself. And obviously fewer people involved in network problem resolution. The alarms can be sent right to BlackBerry or a phone. You can have the map right there. Your maintenance people can have that and go directly to repair the problem. And who can benefit from the application? Obviously, any telecom carrier, RBOX, ILEX, CLEX, metropolitan area network providers, cable companies. There's a lot of banks and financial institutions that have their own networks. Data center owners, utilities, dark fiber providers, submarine networks, and government agencies. So basically, anyone with a fiber optic network can benefit from remote fiber test systems. Any questions or comments? Yeah, the question is, do we use 1625 generally for the test signal? It depends. It is the most common. There's several advantages to 1625 in the fact that it detects microbending earlier, sooner than a 1550 or 1310. Some customers want the test signal to be the same as what it's operating on. So they'll use a dark fiber, and if they're running 1550, they want the test signal at 1550. It's their preference. And you get further distance with 1550. But for the most part, and if you want to do active fiber monitoring, then you would, and you're running at 1550, then you would use 1625, so you're not interfering with the signal. So that is used, that's the most common, is our 1625 OTDR. The question is, in a PON network, this is just going to the splitter location, and that is correct. In my application, I think Ray's covering, is covering beyond. And we would incorporate that technology. It's one of the advantages of the AFCS form. We can work together. If it gets through that point, we can integrate equipment. We do hardware building. So after we get to that point, but yes, most of our customers in the cable, we have a very large cable carrier, and they monitor their backbone network. In fact, that trace was one of their actual network fibers, and they have it down to if the fibers that go to, if it serves 2 nodes, so they go to that, they monitor those, because there's a cost-benefit relationship as well, and that's the way they do it. They just, and then as the technology goes beyond the splitter, then they'll go beyond there. But yeah, you're correct. At this point, our equipment goes to the 1x32.
What's your typical N by M switches that could be used for this kind of?
N by M is going to be, okay, yeah.
We'll get to that.
Yes.
But you make the relay-based kind of mechanical switch, right?
Our switches generally, well, you'll get into the switches, But our system is the remote fiber test system. So the software, the server, the OTDR, and then we partner with the switch people to how the customer would like to test multiple fibers and reroute their traffic. Yes, yes. Yeah, the question is on active fiber, do we need to have a filter on the other end because you've got the 1625 signal going through your network? And the answer is yes. When you're doing active fiber, let's say you're running at 1550, you have a WDM, so your system, your OTDR trace is muxed onto that active fiber, and then before it gets to the receiver, you put a filter which takes the 1625 signal off before it hits the receiver. And then that's your reference trace. And if anything happens in between those points, then you get your alarm and your location and so on. So the answer is yes. You had a WDM on the OTDR side and the filter on the end side. And that's also why, I just want to add one point, a lot of the customers will test like just 4 fibers in a bundle to save costs. They'll dedicate dark fibers, not in a bundle, in a cable, maybe 4 fibers. Some do just one because the assumption, they're looking mainly for cuts, and the assumption is what happens to one is going to happen to all the fibers. Maybe in Texas here too, of course we're from all over the place. There are, like in South Dakota, sometimes they have a problem with gophers that'll start chewing through the line, and they'll just get a few of the fibers. So by they strategically place 4 fibers to do the monitoring, and they'll get 98%, due to the helix factor and everything, 98% of any problem. So there is a trade-off there. Anything else? Okay.
And you said you have to compare, the software works with a comparison, so you have to have an original address as your database.
That's correct. Yep. So you, and we can get into some detail there later, but basically you have your fiber route, you run your OTDR trace, and you make sure it's clean, everything looks good, then you save that, and it shows where your splices are, it shows where your connectors are, and you put landmarks in for various locations, and then you're continually testing and comparing to that reference trace. That's correct.